Hello everyone, this is part 2 of the examples for section 7.2. So now let's go to question number 7. We're going to consider here f from R to R given by f of x equals 2x plus 7. We want to prove that this is 1 to 1. So as always, when we want to prove 1 to 1, we pick two elements. Let's say f of x1, and we say that is equals to f of x2. And then we're going to try to prove that x1 is equals x2. So we're going to get that 2x1 plus 7 is equals to 2x2 plus 7. Notice that we can get rid of the 7s. And so we're going to get that 2x1 is equals to x2. We cancel the 2. And we get that x1 is equals to x2. So we got from our definition here, if f of x1 is equals f of x2, we reach that x1 has to be x2. And this is the proof that is 1 to 1. Now, we also want to prove that this function is onto. And so given y that belongs to R, we need to find x so that f of x is y. Okay? In particular here, if we pick x equals to y minus 7 over 2, then we're going to get that f of x is just 2y minus 7 over 2 plus 7. And notice that this is y minus 7 plus 7, and this is just y. So we found that a specific y, we found that a specific x, so that given any y, I'm going to have back the, when I plug x, I get the y. So it is onto. Notice that this is also the proof that we will use to verify the inverse. This is actually the expression that we will get for the inverse. Remember that for the inverse, what we do is we set up y equals 2x plus 7, and then we pretty much simplify for x. So y minus 7 over 2 is x, and we can kind of say f minus 1 of x is just going to be x minus 7 over 2, changing y by x. Now, to verify that this is true, first we do the composition. F compose f minus 1 of x, which we kind of did before. This is twice x minus 7 over 2 plus 7. And this is going to be x. The 2 cancel with the 2, then the 7 is going to cancel with the 7 in subtraction. So this is going to be x minus 7 plus 7, or x. And if we do the opposite, f minus 1 of f of x, then we're just going to have f of x minus 7 over 2. And that's just simply going to be 2x plus 7 minus 7 over 2. We cancel the 7s. We get 2x over 2, and that's x. Okay, so for both sides, we prove that f minus 1 compose f, and f compose f minus 1 is just going to give me x. Now, let's go into question number 8. For question number 8, we have the function g of n equals n squared minus 4. And we want to prove that is it 1 to 1 or not. And give a counterexample. And yeah, this is not a function that is 1 to 1. And generally, you get a square or a power of 2. It's likely that unless the domain restricts to one single side, you're going to get similar values. So for example, if we do g of 2, that's going to be 2 squared minus 4, which is 0. But if you also do g of minus 2, you also get minus 2 squared minus 4, which is also 0. So there's two different points that they lead to the same place, and they're different. Now, is g onto? No, g is not onto. And the counterexample here is to actually look for an integer that is not going to be produced by this. Notice that because this is n squared minus 4, then you want a number that is not going to be feasible by this. So let's consider minus 2. So you let there's going to be some y. Let y be minus 2. So you get n squared minus 4 equals minus 2. This is not possible because n squared is going to be then 2. And so that will mean that n is the square root of 2, which is not an integer. Okay? So because of that is not possible, and minus 2 does not belong to the range of the function g. So it says, what will you need to change about the domain or codomain to make this function one-to-one? And so to make this function one-to-one, you're likely need to restrict the domain to non-negative integers. So for example, the c plus, or this pretty much will be all the integers positive, 0, 1, 2, 3, and onwards. And so that will make this one-to-one. And to make it onto, you will restrict the codomain to the actual image of the function. So so with this restriction, you make it so is the n squared minus 4, so that n belongs to the integers. And so that will be restricted to a very specific set. That will go like minus 4, minus 3, 0, 5, 12, 21, so on and so forth. With this restriction, every element on the range is going to be matched. And so we're going to make it so it's onto. We got to make the codomain equals to the range. And of course, we're thinking about restricting the domain, so it's one-to-one, restricting the codomain, so it's onto. Okay, last, we're going to go for this proof. Consider f from a to b and g from b to c, and define the composition g compose f from a to c by the composition g compose f of x. It says if g and f are both one-to-one, must be g compose f one-to-one. So proof of good a counterexample. The answer here is yes. So simply imagine that you have g compose f of x1 being g compose f of x2. Okay? So this is just going to be equivalent to g compose f of x1 equals g of f of x2. But notice that when we have this definition, we have that g is equal in two values. So because g is one-to-one, then that implies that f of x1 must be equals to f of x2. This is because g is one-to-one. But now because f is one-to-one, then this implies that x1 is equals x2. So we end up that g compose f is one-to-one. Now for b says f and g are both onto. Must be g compose f onto? And the answer is yes. So let c belongs to c. Okay, which is the final point. So what we're gonna say is we're gonna write this now, and we're gonna think we need to find a, so that g compose f of a is c. But since g is onto, they're going to say a b that belongs to b, which is, by the way, the domain of b. so that g of b is c. So we're going to have that for some point in g that works. But now, since f is onto, there is a that belongs to a, so that f of a is equals to b, right? And so what this means is that g compose f of a is just going to be g compose on f of a, which is just g of b, which is c. So we just find out the specific value that we needed. Now, say C says if G compose F is 1 to 1, must be F 1 to 1. And so it says here, try to prove it directly. And so the answer is yes. And so the way that we go about this is suppose f of x1 is equals to f of x2. Notice that this is because we want to prove that f is 1 to 1. Okay? So apply now f compose g. We're going to apply g on both sides. By composition, so g compose f of x1 is equals to g of f of x2, right? But this is what? This is g compose f of x1, and this is g compose f of x2. But g compose f is 1 to 1. So this means that x1 is equals to x2. So this proves directly what we wanted, because we got from f of x1 equals to f of x2, giving us that x1 is equals x2 by supporting ourselves with g, right? Okay, so this is the end of the examples for section 7.2.